on the size of the input or on the number of networks. The ability to run big nets, big inputs in a way that actually does not degrade the performance a lot. That means there is no tipping point on the size of the model or the size of the input or the number of networks, after which there is a drastic drop in the performance. To deliver such predictable performance scaling, Orca has support for DRAM. Instead of completely relying on the on-chip SRAM and deliver efficiency for nets that fit on the chip, support for DRAM allows to run multiple networks multiplexed over time. We hope this capability brings in much richer AI applications at the edge, where the application requires running multiple models in sequence. Of course, convenience also has to do with how many hoops you have to jump through before you can get something to run. We believe that application developers should be able to run first and optimize later. And while the focus of the first generation of edge AI chips has been on inference, we definitely need support for training in future and even support for mixed precision modes. To plan for all of this and a lot of other exciting features that we have stored in future, Orca has support for floating point mode also, and not just for integer mode. I mean, this is already a rich set of features that differentiate our chip, but these are just like good toppings on a pizza. Let's get to our secret sauce, the support for pruned nets. Pruning has been around for a while, and in general, most people agree that it is a good idea. At the same time, people are disappointed that pruning has not delivered on the gains that it theoretically shows, mostly because there is no good hardware support. Some people are actually skeptical, and rightfully so, as model architectures are still evolving. Maybe small dense models for which already hardware exists, that's the way to go. At Digirum, our status can be summed up as being excited. I mean, we better be. We have been working on this for a while. But the reason for excitement is that pruning does deliver substantial bandwidth and compute savings, as you can see from this plot. For a convolution layer, as the pruning increases, the computation speed up increases, though compared to the ideal one, the efficiency drops when you prune more and more. Of course, any such plot is accompanied by a disclaimer so that people don't get overly excited about what the real gains are. This is just for the compute speed up of a layer. The overall frames per second gains are a much more complex function of different parameters like the network size, number of layers, input size, and so on. But the gains are there. And our benchmarks that we'll publish will show how good the prune nets are. The way we think about leveraging sparsity in prune nets is to think about a class of models, increasing accuracy, decreasing frames per second, and take the high accuracy models, prune them until they are more accurate, but run as fast as their smaller dense counterparts. Or prune them until you get the same accuracy as the smaller dense ones, but much higher speed. Or any other trade-off in the middle. If there is such a class of networks, then for these nets, we can say that pruning is always advantageous. Is this possible for all networks? We don't know. But it seems to be the case. We are optimistic that the AI research community, once knows that good hardware support for pruning is available, would come up with such models. If you remember the beginning of our talk, we promised to talk about our Edge AI platform. And so far covered two aspects of it, the hardware and the software. But an equally important part of the platform are the models. We want to provide an Edge AI platform that gives the best model zoo. And how does the best model zoo look like? It looks something like this. Don't worry, this is not a technical glitch. We have a model zoo with models that run out of the box. In the long run, the best model zoo is actually having no model zoo at all. People should have a tool to port their own models and compile them for different hardware targets. This way, once the hardware is out, all application developers can bring their own models to the table. We have thought about this problem for a while now, and that brings us to the last announcement of the day. We are happy to announce that we'll soon be releasing a tool known as Graphiti. You can use to design, train, port, and compile models for different hardware targets. The GUI allows you to drag and drop layers and design networks. Has predefined subnets that allow for very compact model definition. So not just single layers, but things like residual blocks, inverted bottlenecks, so that when you have to design a big net like ResNet 50, you don't really have to drag and drop 50 layers. The advantage is that after the design, the whole model will come in a single file, and you can export it to standard frameworks such as Keras or TensorFlow. And such a single file allows you to share the model very easily and also debug if you run into any issues. We hope that people will use Graphiti not only port models for our hardware, but also to port models from one framework to the other, compile it for various hardware targets. The tool will be online soon. Conclude, we have presented our hardware, software, and the models. I want to close by saying that if you're an application developer, talk to us. We have hardware samples, sign up for access to them. If you are a model developer, see how you can port your models into a software stack and make it available to a large variety of edge AI users. And if you're a researcher, work with us to see the benefits of prune models realized. We think this is a huge opportunity to design high accuracy networks that are really suitable for edge applications. Thank you.
Hello and welcome back. Thank you, Shashi, for that presentation. We have a few questions that have come in. Bar and also catch up with Shashi later on today at his roundtable. But the first question I'd like to ask you, Shashi, is how do you address performance issues when working with multiple models?
Yeah, yeah, actually that's a very good question. So typically models have to fit on chip so as to deliver very high frames per second. But since we have pruned models and support for DRAM, what we can do is multiplex among models. If you have, let's say, 4 different models, be stored in DRAM, and you can actually switch among them at the same time. So this basically gives you no performance loss, almost no performance loss. So if there's a single net that can run at 100 frames, then 4 nets can run at 25 frames.
When it comes to the range of workloads that the GRAM can handle, can you elaborate a little bit more on that?
Yeah, definitely. So I mean, we have designed it for the edge, but because of the sparsity and scalability that is built into the design, in fact, it is possible to build enterprise level cards. For example, we can build a 16-lane PCIe card with 4 of our ARCAs that delivers essentially 4 times the performance. And not only that, ARCA has a chip-to-chip connection. So that means if you have a big model for which you really want a very good performance, then you can actually slice up the model into multiple parts and actually get more than 2x the performance of the single model, because now both parts are localizable on the chip. So this gives you actually much more than 2x performance. So combined with sparsity, this gives you unprecedented levels of performance for single models.
That's really helpful. Thanks for elaborating on that, Shashi. And just a couple of other quick questions. So yesterday, we spoke a lot about the different methods for compressing models. For example, quantization, just to throw one example out there. So in your presentation, you were speaking a lot about pruned networks. So could you elaborate and maybe compare pruned networks to other techniques to compress models?
Yeah, in fact, our technique works. Pruning and quantization are 2 orthogonal dimensions. So the results that we have are actually for pruned models that are quantized. So you get the double benefit. So let's say, for example, ResNet floating point model about 102 megabytes, quantized model about 25 megabytes, pruned model is about 8 megabytes. Right? So it is kind of an additional gain on top of pruning. So quantization and pruning can both be applied at the same time.
That's brilliant. And one other quick question. You spoke a little bit about mixed precision models. Can you elaborate on why you're choosing to support that?
Yeah, actually that comes to accuracy. So if you work with image classification models or even object detection models, you see that there are some layers that are more sensitive to quantization than other layers. I mean, this is also true for other networks where there could be some intermediate layers that are extremely sensitive to quantization. So for example, in the last layer, which is fully connected layer, if you want to really differentiate between 2 classes, quantization can actually lead to, if the range is not correct or if the real use statistics differ from the when you quantized it, you can have actually saturation for the last outputs. So it is very important that maybe a last layer or a few layers actually run in the floating point mode.
That's excellent. And just to contextualize this, where do you see, which sort of domains do you see the benefit of the GRAM?
Yeah, so our main use case, as I mentioned, is if people want to work with multiple models, it could be multiple applications running on a platform like an AI hub, or even a single application, but that requires multiple nets to run. I mean, even a simple application like, let's say you want to have a surveillance camera that is monitoring who is walking on the pavement, right? So even this actually requires a person detection, segmentation. You have to do a pose detection, maybe a face recognition, just to see if it is a stranger or somebody you know, right? Even such a simple application would actually require multiple nets, and not necessarily each one running at 1,000 frames or something, right? You actually need an always on network that is quite reliable. And on demand, you should be able to run some very high accurate nets at a low performance. It doesn't matter, but they have to be accurate. You don't want to be frequently interrupted by false alarm saying that there is a stranger, and then it just turns out to be a false alarm.
Very useful, Shashi. I'm afraid that's all we have time for, but you can catch up with Shashi and the rest of the Jirian team at their roundtable later this morning / this evening. And we now move on to the next presentation. So Shashi, thank you once again for your time. It was a pleasure having you involved, and see you again shortly.
Thank you, everyone.
Good morning, everyone. To be joined here by Wajahat Kadir, who's co-founder and chief architect at Deep Vision. Wajat, welcome.
Hi, Ben. Hi, everyone.
Good morning. So we're going to run the presentation now for 15 minutes or so. We've got 10 minutes at the end for Q&A. So drop those questions into the live discussion bar, and we'll now turn off your camera, and we'll join at the end of the session.
Good morning, everyone. My name is Wajahat Kadir, and I'm the chief architect at Deep Vision. In today's talk, we're going to take a holistic look at Edge AI acceleration. Understand some of the challenges facing Edge AI deployment, and identify the best system options for deployment. The biggest challenge that Edge AI faces today is the ever-increasing performance requirements. As more and more AI workloads migrate to the edge from the cloud, the performance requirements are increasing rapidly. But edge devices have strict power and cost budgets. As you try to identify smaller and smaller objects, the inference resolution requirements are increasing rapidly. Customers have gone from 720p inference to 1080p inference within a year. And if the trend continues, 4K inference is not far away. Along with the increasing resolution, the frame rates are also increasing. Moreover, customers want to look at the output of not just one sensor. They want to cross-correlate across multiple modalities. However, not all customers want all three at once. Every customer is different, and one solution fits all, it's not desirable. Instead, an extensible solution is needed, which can fit many different use cases. Edge AI involves processing of AI algorithms directly at the endpoints, where the data originates, instead of sending the data to the cloud. Some examples of endpoints are smart cameras, smart gateways, edge appliances. To bring AI closer to the cameras. By embedding the AI into the cameras themselves, the data can be processed at the camera and the latency can be improved. And once the data has been processed, we will only send the AI metadata to the edge server. And AI metadata is much smaller in size compared to the video streams, requiring much less infrastructure investment. However, there's a downside to only sending the AI metadata, which is that cross-correlation across multiple devices becomes challenging. And in some cases, video data may be required to improve results. That's where smart gateways come in. Smart gateways can perform cross-correlation across multiple devices and without requiring a big infrastructure investment. Smart gateways are placed in close proximity to the cameras They consume the video streams from the smart cameras, perform the cross-correlation plus other functions, and then send the AI metadata to the edge server. Smart cameras and smart gateways together present a robust and scalable solution, which is ready to meet the demands of tomorrow's AI. At Deep Vision, we are building AI solutions to power the next generation of edge devices, such as smart cameras, smart gateways, even edge servers. Our solutions are optimized for latency to deliver real-time results, and our solutions can be easily integrated at both the hardware as well as the software level. We are shipping in production volumes, and we are already working on the next generation of our products to bring new and innovative technologies to the edge. Now that we have established that smart cameras and smart gateways are the solutions for the future, what are the challenges? Well, the challenges are that both of these devices have limited power and cost budgets. Smart cameras are powered over Ethernet. After supporting the basic functions such as an ISP, an application processor, video encode and decode, the power budget left for AI devices is much less. It's just 2 to 5 watts. Moreover, smart cameras are very cost sensitive, and the cost budget for AI acceleration is also quite limited. Smart gateways, on the other hand, have high power and cost budgets, but they also need to service many cameras, and they may require significant AI acceleration. Now, because of varying power, performance, and cost requirements across multiple devices, across multiple customers, Deep Vision is building extensible solutions which can scale up or down to meet the demands of multiple customers and multiple devices. Now, what are the system options for bringing AI to smart cameras? The solution of choice is typically a low-end camera SoC. While the low-end camera SoC offers the basic functions such as an ISP, an application processor, video encode and decode, and it also has limited AI functionality. But the AI functionality is quite lacking. Now, the other option is to use a high-end mobile SoC. A high-end mobile SoC offers quite a lot of AI performance compared to the low-end camera SoC, but it is very expensive, making it infeasible as a solution for bringing in which we have connected the low-end camera SoC to Deep Vision ARA1 accelerators. Now, this is a pure play AI inference accelerator. Now, this option offers much higher performance compared to both the low-end camera SoC as well as the high-end mobile SoC. And the cost is much less compared to the high-end mobile SoC, and the power is comparable. Now, let's evaluate these options with the help of a use case. If an AI camera is deployed in a smart city, what function will it need to perform? Well, it needs to perform pedestrian counting, it needs to perform car detection, and it needs the results in real time. Moreover, the smart camera needs to run both of these models simultaneously on the device. And since these models have different performance and at application level. Now, if we own what we observe is that we need 4 low-end camera SoCs to meet the performance requirements of this use case, which makes this solution prohibitive from cost and power perspective. If we only use a mobile SoC, we will need 2 mobile SoCs to meet the performance requirements, which will be an even more expensive solution to the low-end camera SoCs. The best solution is offered by connecting the low-end camera SoC to a pure play Deep Vision ARA1 accelerator. Now, this solution not only meets the performance requirements, in fact, it has performance to spare for future AI workloads. Not to mention the fact that we get a latency optimized solution, which has the ability to run multiple models in parallel with no overheads and provides an easy way of managing gateways, is actually a high-end edge GPU. The AI performance of the edge GPU is quite significant, but it burns a lot of power and it costs a lot more. Now, the other option is to use mobile SoC, which we have just looked at. Well, the mobile SoC is not ideal, but it is a viable solution because it has the ability to decode multiple camera streams. And it offers some AI performance. In the middle, we have a third option in which we have connected the mobile SoC to two deep vision R1 accelerators, once again, pure play accelerators. Now, the performance of this solution is actually higher than the high-end edge GPU, while the cost is much lower and power is much lower as well, resulting in a performance per dollar that is way better than both the mobile SoC as well as a high-end edge GPU. Now, this is where the extensible approach of deep vision solutions really shines. We have built a solution that can go into both smart gateways as well as smart cameras and satisfy their diverse power, performance, and cost requirements. Now, let's evaluate these options with the help of a use case. If we have a smart gateway connected to two cameras deployed in a retail setting, what functions does it need to perform? Well, it can perform video-based activity recognition using a three-dimensional model. It can perform pose estimation across multiple cameras. And once again, latency is of prime importance. Plus, it once again needs to perform these models of different resolutions and performance requirements simultaneously on the device. And there has to be an easy way of managing these models at the application level. If you only concentrate on the performance and once again keep the rest of the requirements on the side, what we observe is that requirements of this workload, which will be very expensive, both from cost as well as power perspective. Interestingly, we need slightly more than one high-end GPU to meet the performance requirements of this workload, which was surprising, but that would make the solution quite expensive. The best solution is offered by connecting the mobile SoC to two deep vision R1 accelerators, pure play accelerators. Now, this solution is also scalable because as the AI requirements of the smart gateway increases, we can add or upgrade the R1 accelerators without changing the SoC. Now, once again with this solution, we get a latency optimized solution, which prioritizes real-time delivery of outputs. It has the ability to run multiple models in parallel without any overheads, and has an easy way of managing the models with different performance and resolution requirements at the application level. So what we have learned in this talk is that we have looked at two separate use cases for edge deployment. And we have found out that pure play accelerators present a scalable solution to meet the diverse performance, power, and cost requirements of smart gateways as well as smart cameras, and present a scalable solution for tomorrow's AI. Now, in summary, we need to take a holistic approach to AI acceleration because it can yield both short-term as well as long-term benefits for system deployment. The requirements for edge AI acceleration will continue to increase as more and more data is generated at the edge. But make no mistake, edge AI is not the same as the cloud. AI performance, power, cost, even physical space are important considerations. We need to build beyond today. Use R1 accelerators or pure play accelerators wherever required, or upgrade them wherever needed, and leverage the benefits of camera SoCs, mobile SoCs, and even GPU SoCs to deliver the best system solution. And that is a philosophy we have at Deep Vision. We are building products for tomorrow's edge, and our hardware and compiler are built to deliver real world requirements or real world use cases. And we are looking forward to working with I would encourage everyone to visit our website. Have a look at the cool demos that we have on the website. We are not only building chips and delivering chips, we're also building very cool modules. And with that, I'm going to end the talk. Thank you.
Thank you, Wahaja. If I could ask you to come back on camera now. Brilliant. Yeah, really interesting talk, and nice to see yeah, some customer use cases or evidence of going in there as well. So we've got a few questions, a couple coming on the chat already. One from Konstantin. How do you orchestrate models, multiple smart cameras in the system?
Multiple smart cameras. So
how do you orchestrate the models? Yeah.
So there's a way to actually manage multiple smart cameras simultaneously. So I'm not going to talk a little bit. I'm not going to talk in more detail, like what the solution is. But we have a way of managing multiple models on multiple cameras, and then basically we can also distribute the load across multiple cameras. In fact, if you have the cameras and the gateways connected, we can also manage the load across the gateways as well as the cameras. But I don't want to go into more details.
Okay, no problem. So thank you for that. Next question from Vlad is, any IPS benchmark results available? Are you talking about those?
So I think at this point in time, we are releasing the results under NDA. So if anybody's interested, I think they can get in touch with us, and we would be happy to share the results that we have. Once again, our results are based upon latency. So, and with IPS, it's like, a slightly misleading number, because I mean, with IPS, basically it can be a throughput-based IPS, or it can be a pipeline architecture-based IPS. But we are focused on latency because that's what we feel is the most important thing at the edge. So but yeah, we would be happy to share the results.
Okay. So reach out to you directly or the team through the event app, and they can
through the
set
website.
Something up with you. Yeah. Okay. Sounds good. So you talked a lot about the hardware there. From a software perspective and this holistic angle, for the developers, to what extent do they need to understand the deep vision technology in order to build models to run on it?
Yeah, so we are focused on inference. So we actually, I mean, the models are developed on the cloud. They are trained on the cloud. And then basically when it comes to doing the inference, that's where deep vision comes in. So we actually pride ourselves on our software, even though the talk was focused on the holistic angle from deployment and whatnot. So what we have is what we do is that we take the model which have been developed, which have been trained on the cloud. We do a conversion statically, right? So we have a full flow, which is a YAML-based flow in which we take the models, we take the data that we need for quantization, we pass it through our tools, and then basically the out comes the binary that needs to be done on the device itself. So we also have a simulator through which the users can simulate their results without the hardware. And the simulator is it gives you exactly what the output would be, and it also tells you what the performance will be, and all of those things are there. And then once you have the models ready, then they can be brought to the device and run on.
Edge AI models increasing significantly in size, or is it a case of running multiple models and more models on at the same time? And how are you future-proofing against that?
Yeah. So interestingly, I mean, every customer is different, right? So some customers do run, or just one model. But typically what we are seeing is that, we are seeing requests for 1080p models, 1080p inference, and not just the video stream coming in. So 1080p 30 is becoming a norm as far as the requirements for inference is concerned. At the same point in time, we do see, I mean, depending upon what sector you're in, we do see quite a lot of models running at the same time. And that's where basically some of our competitors may actually struggle, because I mean, if you have multiple models, you may need to connect multiple chips, but we at dvision do not have that philosophy. What we feel is that basically if you have multiple models running, there should not be any overhead for running those models on the device. So yes, going back to your question, so we do see both the trends, higher resolutions, higher frame rates, as well as multiple models on the device coming from our customers.
Okay, and in terms of future proofing against that, have you got plans for that, I imagine?
Yeah, so I think the biggest challenge on the edge is making sure that as the resolution is increasing, the size of the model is increasing, we have to remain latency optimized, right? So basically what happens on the cloud is that some of the solutions are, or most of the solutions are based on throughput, are focused on throughput, and they can increase the hardware as much as possible, and basically have multiple models running in parallel, or but they'll all be throughput oriented. The challenge for us is to actually make sure that as the size of the models increases and as the resolution of the model increases, we remain focused on latency and make sure that basically we deliver the faster results as for all of these models as quickly as possible.
Okay, excellent. So we've probably got time for one or two more questions here. You mentioned the retail sector in your presentation there. How much can you talk around the sectors that you are operating in at the moment, and which ones are seeing sort of best results and success?
Yeah, so we are focused on retail quite a bit. With retail, basically it comes monitoring of warehouses and monitoring of stores and whatnot. That is also part of retail. And then basically we have the smart retail, which is the cashierless retail. So this is the main segment for us that we are focused on. At the same point in time, we are seeing a good growth on basically both the automotive side, automotive in-cabin, and we are also seeing quite a lot of requests coming in for 5G devices as well. So these are the three main segments, and plus obviously smart cities and smart cameras are always there, right? So these are the 3 to 4 more segments, most of the main segments that you're focused on.
Okay, wonderful. Okay, brilliant. Any other questions from the audience? I think otherwise that might be it. Any final thoughts from you, Wahaja? Anything else you'd like to cover?
No, I think thank you for having me on. It was a pleasure actually covering different aspects of edge deployment, because we deal with them on a daily basis. And many customers actually they migrate, they come to us with their servers, and then they subsequently go to the other solution and whatnot. And what we feel is that on the edge, it's less about the hardware, as long as it delivers the the basic functions such as latency and multiple models and whatnot. But it's more about the software. Even though I do not cover the software in my talk, but my colleagues have covered software in other talks as well. So what we feel is that, what our customers appreciate the most is actually the ease of use from the software perspective, and hardware should just be an enabler for the software. But all in all, edge area is taking off, and we are happy to be a part of it.
Okay, absolutely exciting time. So thank you very much, Wahaja. So for the audience, reach out to Wahaja and the team for any further info. You mentioned there's demos running on your website. You can contact the team and set those up through the Swapcard platform as well. I think we've got over 300 active users on the event platform this week, so make sure you're using that and reaching out to the folks to set those things up. But yeah, for the meantime, thank you very much. And remind us, the audience, we've got some great roundtables coming up later on, so do tune in for those. And thanks again.
Thank you, Ben.
All right.
Hello and welcome back to the Edge AI Summit. Thank you all for joining us for the second day and our second keynote panel, Optimizing for Tiny ML. It's a pleasure to have four wonderful speakers with us today. Unfortunately, Amarjot could no longer make it, but we're in very good hands with Arun, Andrew, Harsh, and Dennis. Don't be afraid to ask your questions. You can put them in the live discussion bar in Swapcard, and Arun will ask them during the panel. But Arun, over to you.
Thanks, Moses. It's great to be here. Hope you're all enjoying the Edge AI Summit so far. A lot of interesting sessions. So we have an interesting panel here, folks from various aspects of the industry. So my name is Arun Rajashekharan. I'm going to be the host of this panel. A very brief introduction of myself, and I would like the panel members to introduce themselves after that. And we have some, I have some questions that I would love the panelists to give their opinion on. And in the meantime, like Moses mentioned, do queue up your questions if you have any. We'll get the panelists to give their answers. So I've been in the embedded space for quite some time, working on silicon communication systems, headsets like the one I wear for a company called Poly, which used to be called Plantronics. And more recently, I've been involved with a company called Edge Impulse. You might have heard about them. They're in the tiny ML space, pretty active. So that's me. Let's hear from the panelists. Andrew.
Yes, hello. I am Andrew Stanford Jason. I'm the principal technologist at Exmos. And I've been in the embedded space for many years. And more recently, I've been working on the co-design of silicon and tooling for that silicon to enable machine learning on the edge.
Dennis.
Hello, my name is Dennis. I'm a senior researcher at Panasonic AI Lab in Mountain View office. So my responsibilities include conducting the research projects starting from embedded devices to more general ML and dataset related issues. Yeah. Nice to have you here.
Yeah. Harsh, please.
Hello, everyone. I'm Harsh. I'm a research engineer at Ford. I work on developing platforms and utilities that enable AI applications, especially with a focus on in-vehicle use cases. And I'm looking forward to our discussion today.
Yeah, great to have the panel here. So we are in different time zones, so if we have a different level of alertness, bear with us. A couple of us, Dennis and I, are in the Pacific time zone. Andrew and Moses are somewhere near the Greenwich GMT timeline, and Harsh is in the Eastern Standard Time. But we are quite keen in talking about optimization for tiny ML. That's if you have not noticed, that's a focal point of this panel session. So just to kick it off, I'll have each of the panel members chime in on why optimization is so important for the concept of tiny ML, right? And I think I would assume everybody here in this conference would in general know what machine learning is about, and then maybe even what tiny ML is about. But I would like to hear from you why optimization is a big deal. So starting with Harsh, why don't you let's go in the reverse order of introduction. Please.
Sure. From an automotive perspective, I feel AI needs to be robust, time sensitive, and power efficient. Given the constraints that we deal with and the real-time natures of our application, if we don't optimize, we are not going to get the results that we want. That is the prime focus, and I think the way you see the automated driving industry proceeding, it seems pretty evident that optimization is a very critical part of our workflow.
Very good. Dennis?
Yeah, sure. Yeah, I think there are two main reasons. First is that unlike the traditional classic ML models, the deep learning models usually operate in kind of layered high dimensional space. So it means that it's kind of consumes a lot of memory and processing. And the second, because of that, the nature of this deep learning models is that there are lots of potential issues when we start to optimize them using just the conventional kind of methods. Just for example, using some just matrix decomposition, but we need to keep more attention for this optimization because, like Harsh mentioned, that may lead to some consequences, especially in the kind of critical applications such as automotive.
Very nice. Thanks, Dennis. Andrew, what do you think from your viewpoint why optimization is key?
Yeah, so for us, it's about getting the most out of the hardware that we have available. So we take ML models and we optimize them on behalf of our customers optimize them, and they can target more model in less hardware when you've optimized it. So reducing memory footprints is quite key. You've obviously got the amount of computation, you want to keep that as low as possible. And so there's the memory footprint of the coefficients, and that can be dealt with quantization, and that's a sort of well-studied area. But then there's the runtime, like sort of tensor arena, how much space you need on your device to actually execute the model, so the temporaries. Optimizing that means you can get more coefficients because coefficients can go in static memory, and the active memory determines the largest possible size model you can fit. So by optimizing, you can get much larger models available to customers.
Great insights. So my general, having heard this question multiple times, so a lot of ML stuff originated in the cloud, compute, and storage, like what Dennis and Harsh and Andrew pointed out, were kind of infinite. So when it has to come to the endpoint, which is where TinyML is very relevant, the constraints are a lot. Optimizing to fit within the constraints is a huge deal within TinyML. Obviously, we won't do it if there are a lot of benefits in bringing to the edge. If not, we'll leave it all in the cloud. It's a topic by itself. We could have the panel keep going in optimization, even though that's a subject of it. I do want us to touch on a few other things in addition to optimization related to TinyML. So the next one I have is probably also a pretty key question. So when, depending on the industry one is in and what they are working on, each one will have their own perspective. So we have folks who are working on the silicon side. If Andrew's on the XMOS, which is very much focusing on silicon, but silicon by itself is not going to give you almost all the times, right, everything, unless it's a completely hardwired silicon, which is very rare. So there's this magical combination of silicon and software. So one is usually static silicon. Once it's fabricated, it doesn't change, but software gives it life. So I want to hear from each one of your panel members. I'm sure you have, even if you didn't work on silicon and chipsets, you have a good idea of what's happening in the silicon space. And even if you're working on silicon, you have to know what software framework, tools, and tool chain allows you to build a model and efficiently deploy. So what is this? What is the right combination of silicon and software? Where do you think we are? Where do you think we are headed? So maybe a few thoughts on this topic. Let's start with Andrew.
Well, so my job is the silicon tools co-design, and I think they are tightly coupled, mainly due to the fact that you can get the most out of your hardware if the software is aware of what it's targeting. So our tools particularly will target our particular piece of hardware, and they're aware of the actual the vector widths and this sort of thing. But a cost that customers have, the total cost of deploying a model is how, if you have the access to designing the silicon, it's the silicon design time plus the tools design time. So there's always this trade-off between I can put more stuff in the silicon or I can put more stuff into the tools. And you have to trade these two things off. And it comes down to availability, and like more you put in the silicon, the more power it costs. The more you put into the tools, the more time it costs. But tools is a one-time thing, and you get it for all the silicon. So it's this constant trade-off that customers have to make.
Yeah, great point. Dennis, this magical combination of silicon and software. Software is like the elastic band, while maybe the silicon is the rigid something under the elastic band. So that marriage is key. So what have you experienced, and why do you think this silicon software combination for TinyML is at today?
Yeah, I can give you the kind of researcher perspective that from kind of my point of view is that so we have to have a software, and the software basically means the PyTorch or TensorFlow, and most of the code for like ML is in PyTorch right now. So the research community is heavily using PyTorch right now. So the question is how to go from the PyTorch to the silicon to the hardware. And there are several ways, like you can use like a standard format like Onyx, but it's not working always. So basically the question for future, which is still not resolved, is how to go from this high level Python, PyTorch, or TensorFlow models to the hardware. And I don't think that you can really spend much effort doing your own software. Somehow you need to integrate into those high-level tools like libraries like PyTorch and TensorFlow. Otherwise, it's not going to be popular. And we work with few vendors, like hardware vendors, and they try to use their own like tools, like Eclipse-based or something like that. But it's really hard for the researchers or like prototyping team to use those tools because they are suited for the hardware people, not for for us. So yeah, so ideally we would like to have solution that goes from the high level PyTorch code up to the hardware. Yeah.
Yeah, that is never a perfect answer, right? I mean, silicon vendors, like what Andrew was mentioning, they do have to provide some software to their customers. Do they do it themselves? Do they have some sort of industry standard stuff integrated? How do device manufacturers and researchers, how do they look at it? That from what I've seen in different industries, not just ML, there is no single, universal answer. Thanks for that insight, Dennis. Harsh, from automotive perspective, even though probably very few automotive companies, except for some here in the Bay Area, they don't dare to do their own silicon, which has never been the case. So it's usually what is available in the industry. So I'm sure you had some insights into different edges, like we talked about. Edge can be as tiny for a fuel gauge versus all the way to now autonomous driving. So what do you think is this? What is happening from your industry perspective, silicon and software combination?
Absolutely. So we tend to consider the system design. AI is one of the component to the system design, and we need to look at the system as a whole rather than the sum of parts. And a critical challenge that we have is how do we scale AI across this multiple edges, like you said, right? We have tiny microcontrollers, we have accelerators, we may have different trim levels. So that is where the flexibility of a hardware and a software solution makes very much of a sense for us.
It's going to be from a Cortex M0, which is probably considered from many in the industry as probably one of the tiniest of edges, because you need some microcontroller run the model, all the way to maybe a NVIDIA or a AMD like a GPU, Tegra processor, whatnot. So software magic, can there be something that scales from that tiny microprocessor to a GPU endpoint? So there's going to be there's a lot of innovation happening. So even in the company I work for, so there are challenges to come up with a machine learning framework that could be scaled. Working with the silicon vendors, so they bring in the least common denominator software capability. I think it was either Andrew or Dennis mentioning Eclipse like IDE, which kind of was revolutionary for the embedded space. And any of you, if you have worked on, years back, embedded space was completely command line interface. And then came the IDE magic where user interface was a lot simpler and compilers and development was a lot more harmonious. So I think we're going through this growing pains, which is going to, but it'll end up, I think, in a very good spot eventually. That's great.
Absolutely. I think once for all networks and software approaches like that, which democratize this scaling, is going to be a big part of the future of AI.
Yeah, AI and TinyML in specifically because like we talked about earlier, it doesn't have too many degrees of freedom because the benefits of TinyML mandates that it is power efficient, cost efficient, size efficient. Great. I mean, another question I have, which kind of is related to this.
So I have another point on that last question.
No, please,
so
Andrew, go ahead.
The question was, what's the right balance of silicon and software? But I think from a customer perspective, they just want an abstraction. They want essentially their model to run. And the silicon plus software, it's the vendor's choice how to set that balance. They get to choose that, and then the customer just wants a standard interface. They want to be able to put their model on the device.
So it becomes completely, so like you said, abstraction is the key word there. They shouldn't have to, most of the developers, application developers, shouldn't have to worry about which chipset the model is running, and you're saying that it should become almost invisible.
Well, so
the software
for instance,
magic.
A vendor could decide, like a chip vendor, I'm going to put enormously complicated hardware, really clever stuff, and then really clever tools. So just loads and loads of things, or a really thin piece of hardware with really super clever tools. But then ultimately the customer looks at that and they say, that's a nice solution. Will it run my model? And they want to know, I don't mind what balance you struck, as long as it runs my model. Please just tell me the power and performance.
So the system is all that matters. End of the day, you're saying, it could be one.
The silicon plus tool, silicon plus tooling is provides the abstraction for the customer. Yeah.
No, that's a great point. So eventually, it just becomes one big blob. How much software, how much silicon becomes kind of many cases, right? There might be some special cases where you absolutely have to use some really dedicated lot of accelerator-based hardware, but most of the cases, it shouldn't really matter.
Or if we look at the say PC industry as very mature, we've got Intel's and Intel's and AMD chips that both are very comparable, and the abstraction is I have a C program, I compile it, and it runs on both. Now, as a customer, I can compare and get all my numbers and really figure out which is the one I want to invest in.
Yeah. Another topic we probably, if we have the time towards then we can talk about it. Normally we talk about one model, which might be the initial challenge, right? Per system, you're running one TinyML model, but the need for running multiple models probably will start evolving, which might put on a different type of optimization challenge, when it's concurrently running. So let's move on to the next one, which is, again, from what you have seen, optimization, right? There are a lot of techniques. Even there were talks yesterday, I think, within AI Summit, techniques used for optimization in software, in hardware. But based on what you're seeing today, I'm sure each one of you are seeing what is in the research community or in academia. Where is optimization headed? Anything that stands out, from your point of view, which can make some sort of a step function improvement in what we see in terms of TinyML or embedded ML, however you want to address it. Andrew, you want to start? What do you see as a roadmap of optimization?
Well, the way I see it is that customers will have an expectation in the future that this this pipeline, so they take their model and they run it through the tools, and it will be very much the way that the sort of control flow industry went. So C program, C++. I want my optimizations. I just want to put -OS, -03, and I get a smaller model. They want to know that their model will run on a device, and they can choose certain optimizations, maybe approximate floating point maths. They're good with that. Or I want 8-bit, 4-bit, 2-bit. They can choose this stuff, and they can do it after the fact, after the training. So like the once for all, like Harsh was saying, one for all.
Got it. So it starts becoming natural. Today, I think the industry is evolving. There are a lot of technology reuse. So feel free to, it doesn't have to be in the same order. Like what, don't feel free to interrupt. It's an open conversation. Yeah, Harsh, go ahead.
So I think I'm a downstream customer to silicon providers, right? So for us, the last part of the ecosystem is to go to the hardware vendor provided tools. Before that, our duty is to make the best model possible. So for us, a lot of effort goes into how do I make these architectures in a way that is most optimized for any edge device? And then we can build on that and leverage the hardware providers tool, right? So with that, we look at neural architecture search and once for all very deeply, because we want our models to be designed in a way that it's best optimized for the edge, and also can leverage the vendor provided software to the best extent. The second thing we have is we don't just scale across different platforms. We also, like you mentioned, Arun, we have to run multiple applications at the same time. So the task of scheduling and making sure that everything runs smoothly is also something we have to consider. So usually it's not just one model, but it's multiple models. So we have to look at it from a systems perspective again, than each individual model.
A great point, Dennis. I think we have a unique panel here. I think each one has a vantage point from which you look at this problem. So what looks so obvious to one might not be that obvious to another, right? So somebody who works on research and application like Dennis, and then Harsh, who has automotive as a vertical, because there are a lot of other verticals too, healthcare, industrial, agriculture. The application might be different and the constraints might be different. So that's going to be, it's like a huge Venn diagram that's taking shape in terms of everything that's happening. So Dennis, how do you see this optimization as a challenge evolving? Is it even from a research community, are you even concerned about beyond proving certain techniques? Because only when you take something into product, making it a product, a lot of times this optimization is going to be standing out. So do you focus on that? Where do you think it's headed?
Yes. I think the basic optimization techniques have been developed like 5 years ago. I agree with Harsh that now we are mostly, from the optimization point of view, we're mostly interested in like neural architecture search, this kind of type of optimization, like a kind of next level. But I guess from what I see in the future, even more important question would be how to make sure that this optimization is guarantees certain properties after we optimize the model. So what I'm talking about like robustness. So for example, unlike the classic models, like deterministic models, ML models are by nature kind of stochastic. So they operate with the distributions. And when we are talking about distributions in high dimensional space, we can easily get the unpredictable results. So for example, for automotive or like medical or some other critical applications, that's going to be really important, because it is impossible just kind of statically check that like inputs, outputs, because of the kind of huge model. So we need to, when we do next level kind of optimization in the future, we can introduce some certain statistical properties into optimization process such that with certain probability we can guarantee this result, or we can detect that our result is not good anymore. Otherwise, without this kind of robustness introduced into the model, and like initially and after the optimization, it's going to be hard to apply such models because it's going to be very challenging for the companies to deal with the unpredictable outcomes of this model.
Mm-hmm. Yeah, no, that's a great point. For those who are listening, audience, feel free to queue up your questions. I think since we have one less panel member than we originally planned, we'll have enough time to accommodate, talk about a few more things. So anybody listening, audience, feel free to queue it up. I think swap card, you should be seeing a window in the right bottom of your screen. So just a reminder. And yeah, please, Andrew.
So other thoughts are, so I can see right now compilers for these specialist hardware are data flow compilers as opposed to this sort of more traditional control flow. I can see going forward a focus, or more of a focus, on control flow for ML. So early exiting models. So the focus will be on, let's not execute the bits of the models that we don't need to execute. Because right now, the general way of doing things is we have a fixed size input, everything gets executed, and we have a fixed size output, where I think that's a very inefficient way of doing it. And even with sparsity and factorization and all these other things, it's still the model of let's just execute the whole lot. Whereas I can see early exits, so cascaded models where we can make easy decisions early and harder decisions later. And I'm sure this will go in the face of, this will go against other requirements like worst case execution time. But I see for sort of consumer products, say on the edge voice recognition, where you can get a very quick response and finish early, turn yourself back off and power down. That's a very desirable property. Or it's much quicker to determine if a sound is voice or not voice than to determine if it's the keyword. Sure, sort of for these voice activated blobs you get in the house. So having an early gate of is this voice allows you to very quickly power down if you hear a noise. So I can see models being built as cascaded series of models, and then control flow being an increasingly important aspect of compilers for ML.
A great point. So the staging different levels of intelligence, which might cost you some sort of latency, but depending on the application, maybe you can mix and match. Fantastic point. I think
just like to add.
Go ahead.
I think control flow, like Andrew suggested, it's really good for embedded devices, but for consumer devices. Another thing is sometimes what happens is you might want to jointly optimize the function, and in those cases, it becomes really challenging to train 3 separate models with a joint loss function or some joint optimization strategy. Those are active challenges that needs to be worked on. And I think there is another challenge, which is data drift, where over time the patterns change and you need to be up to date. So in that case, how do you go about it? Do you update each individual models, or do you jointly train your system?
That's a great point. I mean, there are a lot of challenges. Audience are beginning to queue up the questions. I'll bubble them up. But on this topic, what I would want maybe each one of you, or if any of you have any suggestions as to, there are a lot of benefits in tiny ML, edge ML, whatnot, right? So you're processing the data then and there. I don't think I have to go and explain every positive. The latency is low, privacy is high, whatnot. But is that any big serious challenge or a negative? So I'll queue it up. The bias of the data, it's been a huge topic all along. can the system be easily fooled when you bring the decision making right to the endpoint? What are the things that we are not thinking about today as as could be things that might make the end users start thinking about not bringing ML to the edge and instead leaving it to where it is, even though it has a lot of these benefits, risks. Do you see any of them starting to shape up? And if so, is there anything that's being done by the industry? Any of you, Dennis, Harsh, Andrew?
Yeah, I can comment. So there is such a kind of new topic that is called collaborative learning. So actually we work with UC Berkeley on that, where you can kind of look at the edge and the cloud together and do some small things on the edge that can signal cloud to update the model, maybe because of the data distributional drift in the data or something like that, and update small part of the edge to kind of patch it and fix. And there are a few papers that appeared recently that might kind of try to solve this question and look at the kind of system level, not just the kind of traditional researcher point of view where you're kind of narrow focused. Yeah.
Great point. Andrew, Harsh.
Well, so I feel like we're drifting from optimization, but I feel edge poisoning of cloud models is an issue that will need to be addressed going forwards. So the ability to inject false data into your cloud model through the edge will have to be protected against quite cleverly.
Mm-hmm. You mentioned two things, drift and edge poisoning. That's an interesting way to put edge poisoning, but it kind of loosely ties back into optimization. If the data is going to drift, you optimize a model for something specific, and if there's too much of a fit, so it's not directly optimization, maybe efficient model or inclusive model or resilient model, but indirectly optimization might come into play because you optimize it for few boundary conditions and not accommodate other things. So, but I do agree that we're not strictly talking about optimization itself, but it's related to TinyML, data drift, data bias, which might lead to the edge-based ML to be easily fooled because it cannot take into account of the computer vision problem. For example, could somebody just flash a smart photo in front of it to fool that system, while that same computer vision challenge, if it was being, if the model were to be running in the cloud, it will have way more powerful capabilities to not get fooled. So there are topics that we could easily get each one's opinion on, but that's something I thought. Let me bring up one of the first questions that came up from the audience. The question is, can you comment on model portability across products from multiple SoC vendors? Can software, hardware be developed independently, right? Like XMOS, you do whatever software you do need to do. I think the question is around, can I just take software from some other entity and marry it? So Andrew, you talked a little bit around this. Why don't you start with your response?
So yes, I think they can be developed independently. I think this is, again, down to abstraction, and tool chains like TVM and MLIR are providing a lot of tools for handling this problem. But right now, the industry is it's fairly immature. It's very innovative and lots of things are going on. So lots of vendors are producing interesting pieces of silicon that can do magical things. And it's down to them to target this. And if it goes as the sort of x86 industry went, over time, these things settle down and standardize, and then the tools really mature. And the tools provide the abstraction that individual chips need in order to efficiently target their chip. So we can do that now, but it's a lot of work. Over time, the cost of updating tools to target new chips gets lower.
Great point. Dinesh, Harsh.
I feel like there are some initial efforts being made. For example, Onyx was a good starting point. Certainly, it's not great. It's not the best, But then there are other efforts such as OpenVX and NNEF, which are trying to address those problems. But I think it's like Andrew said, it's a function of progression and maturity of the technology.
Mm-hmm. Yeah, please, Dennis.
Yeah, I would say like ideally you would develop them like together, like what is like Apple doing, Google are doing, and other kind of big companies. But if you're kind of a small company doing hardware, I guess that's what is assumed that, yeah, you kind of need to hope that compilers like TVM or something will solve the problems. But yeah, it's still a kind of gray area. There is no good answer, unfortunately.
Mm-hmm.
We've got kind of a hardware lottery situation going on as well, where over time, like hardware gets made, it gets adopted, the compilers get better at targeting that, more people make hardware like that, the compilers get better, and we get to a point where the industry has matured. Right now, there's a lot of room for innovation because it's a young subject with lots of, like, no one knows what the best model is yet. No one knows how to, like, Transformers came along and everyone went, oh, that's nice. And then like CNNs, that was a big deal.
Yeah.
And over time, these like inductive biases are making the models more powerful, but no one really knows what the minimum entropy model is. I feel we're probably quite a long distance from where we're going to get to. Like, we still have these perceptrons connected to each other with some activations, but they're connected in particularly regular forms, and it's unclear whether that's a good idea or a bad idea. Or I think over time these priors will develop, and the architectures will settle down.
Yeah, yeah, no, great. I mean, yeah, that is that's the innovation phase in the early stages. Whether it's in-memory compute or neuromorphic compute, that's one of the audience. He's asking, how do we see neuromorphic chips changing tiny ML systems? So that's kind of points to what all of you are talking about. Each layer is trying to figure out, which applications, which end market will ideally use them, whether it's computer vision, voice, audio, sensors, because the industries are so broad, applications are so broad. It might take a while for the standard deviation of all this to come in and say, this is the best silicon architecture and software to converge on it. So that's why this abstraction, I think what Andrew is talking about, if it can accommodate good majority of the silicon space, that by itself is problem more than half solved, while there'll always be special hardware and special software in both edges.
So I don't think there'll be a best, but there will be many bests.
Mm-hmm.
So automotive and consumer and like tiny edge wearables, they're all very different requirements.
Mm-hmm.
But I kind of imagine that the underlying hardware, the multipliers, whatever the architecture ends up being, will somewhat standardize. And it may be automotive has a lot of copy paste of a very small wearable, maybe with a bit EC, but it's going to be fundamentally very similar.
Yeah, yeah. So I mean, I used to be in the silicon space for quite some time. The general shift I've heard some industry experts way more seasoned than me talk about is what we are transitioning is this general purpose ISA architecture, right? And now we are going to this deeper and deeper domain specific architecture. It's called DSA, where you have logical firmware or software handled by a specific engine, signal processing, which is kind of the precursor to a lot of this machine learning stuff, having its own engine, and then neural acceleration. So each harmoniously doing the best of what they can do. Would that go deeper in that domain, or would it become one single blob of silicon again, right? And all these are sometimes like pendulum, they swing from one extreme to the other. It's yet to be seen. I'm sure Andrew, who's in the silicon space, sees this debate happening probably every other week. So there's another, again, maybe a question that we kind of touched on. So the question is, can you speak on some of the biggest challenges of optimization? Easy said than done, right? Whenever anybody needs to optimize something, it's never trivial. I don't know if we have enough time. The chat window just closed, but until Moses tells us something, we can, we have, I think, till another 5 more minutes, probably. Or is it not, Moses?
We're just about to hit time, but maybe a quick 30 seconds from everyone
yeah,
on that last question. So
yeah,
everyone, as concisely as possible.
Well, a challenge. Is it 1, 2, 4, or 8 bits? Don't know yet.
Good, great. Yeah, that's a great way to put it. Dennis, biggest challenge?
Yeah, I guess I can just summary that. So we need to think about probabilistic models, and the challenge is how to incorporate probabilistic nature of AI models into the kind of our optimization. So it's not like 1, 2, 3, it's 1.1 with certain standard deviation.
Harsh?
Yeah, I'd agree with Dennis. Robustness is a big challenge for optimization.
Awesome. Yeah, it's great. So I think we are out of time. We could stay here for hours, and this is an awesome topic. Thanks, Andrew, Dennis, and Harsh for a wonderful conversation. Yeah, Moses, please take it away.
And thank you, everyone, for moderating. It was a really interesting panel. And you can catch up on some of these issues of bringing AI from the cloud to the edge, and maybe to the tiny ML space, because the edge is quite loosely defined, but here we're specifically talking about tiny ML. We've got some roundtables happening within the next hour, so do tune in for them. They're very interactive, and you can use Swapcard to network with Arun, Andrew, Dennis, and Harsh, and set up some meetings to learn more. But thank you so much for your time, and see you again shortly for the next session.
Yeah, thank you.
So welcome back to our next session. We are now joined by Moshe Mashali, who is co-founder and CEO of Deep AI. For anyone that missed it yesterday, Moshe was actually part of yesterday's keynote panel, which was around building scalable edge AI systems. Really great discussion. So I'd urge anyone, if you've not managed to catch it yet, go back, watch it on demand. Really, really worthwhile watch. A little later on this morning, so at 11 a.m. Pacific time, Moshe is also going to be taking part in a roundtable discussion, which surrounds whether to train AI on the edge or on the cloud. So make sure you register your attendance for that in advance. Places are very limited. So for today's presentation, Moshe is going to be discussing Int8 training and the edge AI is now truly possible. So as always, if I could ask you to please pose your questions to Moshe in the live discussion box at the bottom right hand of your screen. We'll be returning for some Q&A live at the end of the presentation. So without further ado, I'm going to hand the stage over to Moshe.
CEO of Deep AI, and today I would like to discuss edge AI and the possibility to do the entire life cycle of edge AI application, in other words, training and inference, perform both of them locally at the edge without sending data outside the edge. And this is possible using a technology that we have developed, Int8 training, and I will explain this during this talk. So AI applications are quite unique in the sense that the applications have two types of workloads that need to be continuously running together. So there is a training part in which we feed the system, we feed the network with label data, and we correct the behavior of the network. We teach the network how to respond to this data. And of course, training is the complex part of teaching someone like a neural network, teaching it to do a certain task. And there is the inference part, which is the production workload, running the system on unseen data again and again, on unseen data, in order to get decisions. And since the data is dynamic and the environment is changing, we have to keep training the system on new data all the time in order to keep the accuracy high. Now, training is done today on data centers, and it requires GPUs and large ASICs, and the power that is consumed by those GPUs is very high. We are talking about 400 watt today and even more. And this is mainly because training requires floating point. It is done on a floating point precision. So all the computations are very complex and require a lot of energy. And we see some attention in the public domain to these energy aspects. We need to put some energy label for AI. This is one quote, for example, and there is a lot of environmental issues, environmental concerns are coming into considerations, whether it's justified.
Have been improved over time by the research community, academic community, getting to extremely accurate models on the very large problem of ImageNet with 1 million, more than 1 million images and 1,000 classes. And what we can see here that in all of these networks, the data remain the same, the ImageNet 1K as we call it, and only the model and the training techniques have been changed in order to get better accuracy. So while everyone is running to get better accuracy, and here we can see another example, for example, in object detection, there is another elephant in the room that we have to consider about the size and the computational complexity of these models when we want to take them in production. So accuracy is not the only metric that we have to take into consideration. And when we take also the latency into account, what we see is that we can put all the models in the world on what we call efficiency curves, where the accuracy is on the y-axis and the latency is on the x-axis. And here's an example for T4 GPU of NVIDIA, a trade-off for ImageNet classification problem with many types of model, including quantization and other techniques that we are going to talk about very soon. So what we can see here, that the red line represents something that we call the efficient frontier, the best achieved trade-off between accuracy and latency spanned by existing models that we all know. We can see EfficientNet, ResNet family, MobileNet, and others. To give another motivation about the complexity of optimization of runtime for edge devices, what we can see here is what happened when we take ResNet 50 and EfficientNet, and on the gray, we see which one of them performs better on latency on K80, but the blue is V100 GPU. We're talking about inference performance. And what we can see here is that on K80, the EfficientNet is more efficient, is running faster, but on the V100, ResNet 50 is actually a better model in terms of latency. This motivates us that the models have to be optimized for the specific hardware that we are having in a way that should take the hardware consideration into account while designing a specific model. Because one model that is fast on a specific hardware not necessarily will be as good as on a different hardware. And let's talk about something that we call the inference optimization stack, which is a kind of a pyramid that we draw, where at the bottom we have the inference hardware. We can see here GPUs, FPGAs, embedded hardware, CPU, TPU, and others. On top of that layer, we can see the runtime engine, which simply graph compilers and drivers that is used to run the inference. So those, for example, are TVM, OpenVINO by Intel, TensorRT by NVIDIA, and others. On top of that, we can see quantization and pruning, which are well-known techniques to improve the inference performance. And on top of all these layers, we see the model design. So the model design kind of affect the performance, but it has to take into account all the layers below, like what is the graph compiler that we are running, what is the hardware that we are running on, and whether we are doing quantization or pruning or not. So these are kind of the components of the inference stack. In order to optimize, we need to use the best tools that we can have in each layer. And there is an interplay between the layer, as we've seen in the previous slide, that a model that is designed for a specific hardware won't be necessarily a good model for a different hardware. So all these components have to be kind of combined together to get good inference performance for each specific scenario, hardware, graph compiler, and quantization level. Let's go back to ResNet 50 and see an example. This example is a screenshot from our platform where we can see the accuracy, all the performance characteristics actually for that model. So we can see here the accuracy, we can see the throughput, we can see the latency, memory footprint, and the model size. If we go to the next slide, what we can see is that by optimizing ResNet 50, we can get an improvement of throughput, latency, and also model size and memory footprint without compromising on accuracy. And here are kind of the numbers before and after the optimization. Now I'm going to talk about how can we achieve such optimization and what is the characteristics of solution that can provide such optimization in the model design space. So how can we design a model that is running faster on a given hardware? So first of all, we have to consider algorithmic solution. Quantization, compilation, and all of those are not the only solution in order to optimize the runtime performance or the inference performance. We have to also think about the model itself, the model design itself, the number of layers, the number of neurons in each layer, and the connectivity of that model. And designing neural architectures is a very complex problem that we are going to talk about it in this session. Accuracy should be a key that drives us. We don't want to compromise on accuracy. It should be hardware aware, and I think that I gave the motivation why. And it should work with our current tools. We don't want to have a new stack of tools. We want to work on PyTorch, on TensorFlow in the development, having ONNX, TVM, OpenVINO, TensorRT for the deployment, and we want to have an end-to-end approach that can take a trained model, optimize it, and get it to production. We are going to talk about neural architecture search, which is a family of algorithms that optimize the structure of the neural network in order to get specific characteristics. So neural architecture search started in 2017 at Google with a model that is algorithm that is called NASNet. It kind of found the state of the art for ImageNet. For that time, it was 83.1 top 1 accuracy on ImageNet. Then they used mobile NASNet. It's a platform-aware neural architecture search, which simply try many architectures and train them based on a very clever cost function that kind of combine the accuracy of the model and the latency of the model. After that, we saw a different approach of differentiable neural architecture search, the paper that is called DARTS, with kind of knobs that define a range between 0 and 1 for each sub-architecture in a hyper network, that optimizing those 0, 1 parameters will converge to the structure of the neural network during the training of the model, which is significantly more efficient than what we saw with NASNet and MNASNet, which were brute force, let's say, algorithm driven by reinforcement learning. EfficientNet and MobileNet V3 are examples for neural architecture search algorithms that provide neural networks that also take into account the performance as part of the optimization objective. Here on those papers, they are using the flops, the number of floating point operations, as a proxy for the performance, which is not a one-to-one ratio, especially on hardware accelerators, but this is something that we will talk about soon, about how can we optimize the specific parameter or objective that we're interested in a neural architecture search algorithm. So if we look on the trend, we are moving from exhaustive search to faster methods, from looking only on accuracy to looking on the trade-off between accuracy and efficiency, and from classification to having all the tasks. What we are going to talk about is AutoNAC, a proprietary algorithm that developed at DESI, which is from the family of neural architecture search, which simply find a model to perform better in terms of latency for the inference on a given hardware, while taking into account all the layers below in that inference stack that I just presented. So in that algorithm, what we need as an input is 3 components. One of them is the user dataset D. The second thing is a baseline model. Let's say that we are starting from ResNet 50 for classification, and access to a target hardware age. AutoNAC objective is to find a new neural architecture which denoted as A star that preserves the accuracy and maximizes the throughput. In this example, it can also minimize the latency or minimize some power consumption characteristics in the edge, and any measurable performance objective. The AutoNAC is aware for the data, the hardware, and low-level graph compiler and quantization techniques. The formulation of the problem that we are trying to solve is finding A star, which is argmax on the throughput on all the neural architecture search space, which is denoted as a calligraphic A, maximize the throughput on the hardware for the neural architecture A, given the data D. And why do we need the data D? Because of the constraint that we see here, that we want the accuracy to be at least as good as the A0 architecture, the accuracy on the A0 architecture. And what we can see here is the accuracy throughput trade-off. That simply what we want to do is preserve the accuracy from the baseline model A0 to A star with AutoNAC and getting better frame per second or better throughput. In this example, as I mentioned, it could also run on latency minimization or power consumption minimization. So how can we do all of this? the tricky part is that term, but let's first start with the throughput. If we have a search space of thousands of neural architectures that we want to consider, which are different in the number of layers, number of neurons in each layer, the connectivity, the types of the layers, the activation function, etc. Measuring the throughput is relatively easy. We just need to connect to the specific hardware, in this example an edge device, and measure how the neural architecture performs on that hardware in a concrete measurement that we can measure the throughput, we can measure the latency, and D, which is the data, is actually not needed here because we can measure the throughput and the latency with random weights on initialized neural architecture without training it. The more complex thing is how to estimate or how to know that the constraint is valid. And this is kind of the secret sauce in AutoNAC, which simply an approximation technique for that term of accuracy of a neural architecture given a data, but without training it. Because if we want to search on thousands of architectures, we can train each and every model in that search space in order to converge for that optimization function. So what we have to do is kind of having an approximation, a good approximation for what will be the accuracy for a given neural architecture and a given data. And if we can use machine learning model, which is simply what we are doing, in order to estimate this term, we can know if the constraint is valid for a given neural architecture, and that's led us to converge very, very fast, something that is 2 orders of magnitude faster than every other neural architecture search algorithm that I mentioned earlier. So this is kind of a diagram that shows that we need the baseline model, the data, and the inference environment. We put all of them into the AutoNAC engine, and we get the output, which is the optimized model with a new structure compared to the baseline model that performs better and kind of satisfy the optimization problem that we showed earlier. Few properties of AutoNAC. It improves the state of the art, and I'm going to give examples for edge devices like NVIDIA Jetson in a moment. It's operates on top of TensorRT or any graph compiler and quantization technique. And for every accuracy point, AutoNAC can find the fastest architectures and can operate in order to optimize that input neural architecture. Moreover, AutoNAC is a fast algorithm, as I mentioned, because we don't have to train each and every candidate in the search space. We can run that algorithm in 2 orders of magnitude faster than any NAS paper. And let's talk a little bit about our results. So you're already familiar with that type of graphs. What we can see here is a classification problem running on ImageNet, where on the y-axis we see the accuracy, top 1 accuracy on ImageNet validation set on that example, and the latency is on the x-axis. And if we consider efficient and B0 as our baseline model, what we can achieve here is having a model that is about almost 3 times faster, more than 2 times faster, and even a little bit more accurate because it satisfies the constraint that we saw in the optimization objective example. So for each and every known neural architecture, we can have a DesiNet model that is both running faster and more accurate in its accuracy. And this kind of defined a new efficient frontier for classification on ImageNet on the Jetson hardware. So this result is very promising, and we have graphs like that for any computer vision task, like object detection, semantic segmentation, etc. I will be happy to take any question if are there here in the audience, and thank you very much.
Thank you, Jonathan. Bang on time. Really interesting product you're showing us today. A question from me actually is, what type of hardware can this solution be used for or implemented on?
So since we use concrete measurements on the hardware, as I mentioned in the algorithm, we can connect to that solution any type of hardware. We so far support NVIDIA, all the types of NVIDIA hardware through TransORT, all types of Intel hardware, mobile devices, Core TPU by Google, and almost any edge device that is in general availability can be easily connected to that optimization engine. And there's no properties or characteristics of the hardware that need to be hard-coded into the algorithm in order to do the optimization. Only an access to the hardware in order to do the measurements is needed in order to run the AutoNAC algorithm.
Yeah, that's brilliant, Jonathan. And another question, you mentioned reducing GPU hours, but could advances in the inference optimization stack mean that eventually we will no longer need GPUs for accelerating AI workloads?
A good question. As we saw in the curves that I mentioned for GPUs, we have similar profiles and performance characteristics for CPU. And what we can see is that CPU is still a bit behind the optimization that we can achieve to GPU, but we definitely can push the CPU performance to a level that it will satisfy most of the workloads that need to be run for computer vision. Obviously, it depends on the specific workload, but I think that everyone is can agree that if we boost the performance of CPU by a factor of 3 to 4x, it will get to a meaningful point where the use of GPU is less needed for most of the inference application, and we can let people use CPU in more and more applications, especially in the edge where it's more available and accessible.
That's brilliant. And I'm just building on that. Which types of workloads is your solution best suited for?
So at the moment, we're supporting all the computer vision applications from classification, object detection, semantic segmentation. We are now entering into the NLP space to work on BERT models. So we have some results on BERT that are boosting by more than 2x some of the famous BERT models without losing any accuracy. And we will soon enter into the audio domain for audio processing and transcribing.
And we have a question from Gaurav. Like, do you use knowledge distillation methods during optimization?
So which don't change the training technique. So if knowledge distillation is used to train the baseline, we use the same baseline, the same training technique that used for the baseline. But our core technology is not based on knowledge distillation. It could be added as a bonus. So you can use that, but the main achievement or the main improvement is not getting from knowledge distillation, but more from a better design for a given models. For example, in NLP that I just mentioned, knowledge distillation is kind of the go-to. So we compare models that use knowledge distillation like DistillBERT, for example, and we can use the same training like DistillBERT is trained in order to get the same level of accuracy with a model that is 2x faster. So if knowledge distillation is already used, it will make sense to keep it also to train the DESI optimized model. But if not, you can add it, but you can also not add it.
That's brilliant. And we have a couple more minutes left. And you touched upon this briefly before, but can you elaborate more on the domains you are seeing the most applications of neural architecture search and why those domains in particular?
Yeah, so basically taking computer vision to run in the edge requires a designing of the model kind of from scratch because every data is different. For example, the feature that we are seeing now, the virtual background on Zoom, uses semantic segmentation algorithm that is running on my laptop at the moment. if you consider a low-end laptop, you will not be able to run that feature. Enabling computer vision to run on the edge is something that we are focused, and this is where the Autonac technology is giving the main boost at the moment. Running a standard computer vision model without changing it on the edge will probably not be the smartest thing to do. Also, what we see is the data have a very significant role. So as we saw, the DesiNet has been optimized to ImageNet, for example, but each data for each customer and application is different. And the neural architecture also have to be optimized for a given data in order to get the best results that can be achieved.
That's brilliant, Jonathan. Thank you so much. And that just brings us to time. So we only have a few seconds left. But you can catch up with Jonathan through the Swap Card platform. You can reach out to him and connect and ask him questions based on what we've learned today. And also we have some amazing roundtables. These are interactive discussion groups. Do join them. The first one is on how to bring models from the cloud to the edge, so highly relevant, and it'll be very interesting to hear all of your opinions. So do tune in for that and ask your questions. Jonathan, thank you so much. Really interesting presentation and some really great insight. So thank you once again, and see you again shortly.
welcome back to Edge AI Summit for the next session. Delighted to have Mike Hemery join us back on stage. We'll be at the virtual stage at this summit this year, talking about some of the advancements in analog compute. And I know, Mike, that you've been talking about a new product today, so look forward to hearing about that. And with that, we'll get straight into the session and then look forward to the Q&A at the end. So Mike, I'll hand over to you.
Thank you everybody for joining. It's great to talk to you all. We're proud to be sponsors and past participants of the Kisico AI Hardware Summit series. Now, a few years ago when we started presenting at this conference, we just had a test chip and a really firm conviction in our analog compute technology and the edge AI markets. Now, since then, we've used these conferences to show that our technology works, to launch some really compelling products that are now in customers' hands. And we have a tremendous belief now at Mythic that we're onto something really huge here. Now, in case you missed it back in September, we had a booth at the AI Hardware Summit down in Mountain View, and we had a great time. It was really great to get back to doing in-person conferences. And people got to see our hardware running on a variety of platforms, and we were running 2 demos, a YOLO v3 object detector and an open pose detector, entirely in our silicon. And everybody got to see the really great latencies we were hitting, running without a fan, and again, we were just really happy to have people interacting with our hardware. But we're back to being virtual, so let's make the most of it. So I'm going to talk about Edge AI, and we're actually going to announce a new product. So what sets Mythic apart is our analog compute technology. It's very unique and disruptive. And now it's proven and productized and in customers' hands. And we're hitting best-in-class latency and power by a very good margin. But that's not the only reason I'm excited. I have the privilege of seeing the development work that's happening far down our technology roadmap. And I know that the long-term potential for this technology is incredible. And I'm really excited by the possibilities of the analog compute technology in the coming years, of what we can enable in compact, low-power silicon for Edge AI. Another reason I'm excited is the markets. When we started the company, there really wasn't a well-defined Edge AI market, and we just had a lot of belief based on logic and the macro trends. And when we talked to customers, we could tell they were still getting educated about what value AI could add to their product. Now, when we talk to customers, they know exactly what they want. They're looking for the right solution to run AI at the edge that hits all their pain points in terms of performance, cost, and power. And we have engagements across the spectrum of markets shown here. And that really shows that AI is a generic and powerful tool. If you build the hardware and a powerful software SDK, you can hit a lot of compelling markets with a relatively modest scope of the overall product. So let's first start with the problems that we're solving with AI at the edge. There are a lot of reasons why we want to run powerful AI models at the edge and not in the cloud. The design is simpler, the privacy is stronger, and the overall experience is just much better for the end customers. But the edge means millions of devices, concerns about cost and bill of materials, battery power, and tight enclosures with really strict heat requirements and no fans allowed. This creates a lot of new challenges and requirements that you don't see in the data center. So CPUs, GPUs, TPUs, FPGAs, they tend to only solve some of the challenges shown here. Only analog compute technology allows you to solve all of these challenges. So let's first talk about performance. Customers want state-of-the-art models running at high resolutions and high speeds. And we're also seeing a big rise in demands for concurrency. So either models running in parallel or the results of one model feeding into a second model. And latency is also top of mind with customers. For applications like AR and VR and autonomous systems, we're actually seeing very aggressive latency requirements, sometimes below 10 milliseconds. And don't be fooled by big frames per second numbers from other systems. It's actually batch equals 1 end-to-end latency that customers are looking for. And they're not getting it out of systems that are out in the market right now. Now, to hit latency in the 1 to 30 millisecond range and have multiple models running in parallel, DRAM is not going to work. The weights of the model need to fit entirely on the AI coprocessor chip in order to hit these performance requirements. And this means you need a lot of memory capacity for weights, and you need a really high bandwidth with that memory. Now, SRAM can deliver that bandwidth, but it's very expensive and power hungry. As we'll see later, this is actually where analog compute combined with non-volatile memory like flash really shines. All right, cost. Now, customers generally have a specific budget for hardware and their end deployment devices. So not only is the performance per dollar critical, but it's also important to have a range of product available for all the different price points you're going to see with customers. And size. Now, the edge is about compact spaces. So no giant heat sinks, no fans. You need to be able to fit a single chip into a compact environment, or you need to be able to pack these chips onto very compact PCI Express cards. So single chip solutions are key. And then finally, power. Power is not just important for battery-powered applications. Even for wired applications, customers care a lot about heat. So for single chip solutions, we're seeing 3 watts or less as the sweet spot for wired applications. For battery-powered applications, we're seeing demands well below 1 watt. So now I'm going to talk a little bit about analog compute. So analog compute has been around for a long time. In the early days of computing, it actually coexisted with digital computing because it was significantly faster for certain problems. However, there was a major issue with it. The power consumption and cost of compute and storage elements were just far greater than digital. So eventually digital caught up and analog compute became a thing of the past. But now when AI came around, it was clear that the compute requirements of AI were far outpacing what digital can deliver. And this is where we dusted off analog compute and pioneered a method of combining it with flash memory. And when we combine it with flash memory, we get incredibly compact compute and storage in a single transistor. So we've solved the major challenges that held back analog compute. We can store a single 8-bit value on one flash transistor. That is 50 times denser than SRAM. So that's storage. What about compute? Well, we don't actually have to read the values out of memory in order to do matrix math. We can pump electrical currents into the flash memory array. They will naturally multiply based on the value stored in the cell and then add when they all hit the common vertical bit line. So now you have multiplication and addition, the basic building blocks of matrix math. And because this is operating in the analog domain, it's very low power and incredibly fast. We then wrap this block up with ADCs and DACs so that it looks like a digital block for the rest of the architecture. Now there's also a very unique aspect when it comes to power consumption with analog compute and flash memory. Remember that flash memory can retain its state with no power applied. So we can quickly remove the power to the flash memory blocks and to the analog circuits and then turn them up instantly. So this means you get instant on-demand compute and you get a near zero power sleep state when no work is being performed. So this means our total power consumption of the chip actually scales linearly with the workload. We're in a 40 nanometer process that's very low leakage. So we actually have far greater power efficiencies when you have moderate workloads compared to the digital solutions out there. So the big news we announced this year is that we solved all of the immense challenges of turning analog compute into a real product. And we announced the M1076 analog matrix processor, or Mythic AMP. Each Mythic AMP has 25 teraops per second of AI performance using our Mythic analog compute engine. And this is a tile-based architecture. So we have 76 tiles on the chip. Inside of each tile is an analog compute engine with capacity for more than 1 million weights. And each tile also has a RISC-V processor, conventional SRAM, and a digital vector engine. And you actually map AI applications to different regions of tiles. And when you do this, you get both concurrency and you get deterministic execution. So at compile time, you know exactly how long execution is going to take. This is also a DRAM-free product. So just the single chip alone is enough to deliver really powerful AI. Now this chip burns about 3 watts of power and it's manufactured on a mature 40 nanometer CMOS technology. A really nice thing about our architecture is that the host driver is very lightweight platforms. So here you see our M.2 AE key that was first running on a NXP IMX8. Here we're showing a Qualcomm RB5, also with our AE key chip. Now this is an NVIDIA Nano with our M key. And there's an NVIDIA NX also with our M key on it. And finally, the NVIDIA Xavier AGX. And here we actually have 2 of our M.2 cards plugged into it. So you can really easily scale up the compute by plugging in multiple cards. This is a really key point to drive home. We don't ask our customers to change the host platform. A lot of our customers are very happy with the host they're using. What we're giving them is the option to augment it with a lot more AI compute. So you could take something like the NVIDIA Jetson Xavier NX, which has 21 teraops per second of AI compute. Now, in reality, when a customer is using that platform, they might be doing a lot of other things on that system, so that 21 teraops may not even be available. Or maybe the 15-watt mode is just way too much power for the customer, and they want to operate at a much lower power mode. Well, they can plug our chip into the solution, or they can plug multiple chips into the solution and have a lot of scalable add-on compute power. And this has been very attractive for customers. We were actually working with customers across all of these ranges of platforms, and they're very happy with this ability to add in compute performance. Okay, now on to a new product announcement. I'm pleased to announce the Mythic Quad Amp PCI Express card, the MP10304. So this is a compact, half-height, half-length PCI Express card, and it has 4 of our Mythic amps on it. This really highlights the flexibility and scalability of our tile-based data flow architecture. So to the host, this appears like a chip with a much larger capacity, 304 Mythic amp tiles, 100 teraops per second of AI compute, and capacity for up to 320 million weights. Now the typical power of this card is under 25 watts, and it's got a 4-lane Gen 3 PCI Express interface. So now let's talk a little bit more about the use cases with these quad amp cards. So think about a small autonomous system that's very power constrained, but needs to run a lot of complex applications in parallel. So in this case, this little robot is running scene segmentation. So it's determining where is the road, where is the sidewalk, where is the grass. It's also doing object detection. So it's looking for people, it's looking for cars, it's looking for potholes, it might need to read street signs. So it has to do a lot of things in parallel in order to navigate the world. So that's a pretty complex application. It's actually easier to wrap our heads around something a little simpler. And this is actually a use case that we're seeing with some of our customers. So this is an object detector feeding its results into an object classifier. So object detectors are very good at localizing objects within a camera and drawing a bounding box around them, but they have a fairly limited ability to have a broad set of classes. And often they can get a little bit confused about the exact object it's looking at. Object classifiers, like ResNet 50, can detect up to 1,000 classes. So they're very good at determining what type of object it is, but they're not capable of actually localizing them within the camera. But if you combine the two together, you actually get the best of both worlds. I'm showing a pretty simple example here of an object detector on a traffic camera bounding box the cars and then feeding it into a follow-on classifier to determine the make and model of the car. So it sounds somewhat simple, but now think about the complexity of actually implementing this. You have an HD resolution neural network running at 30 frames a second. You might find anywhere from 10 to 100 objects in each frame. You then have to run a follow-on classifier, which itself might be tens of billions of math operations on each one of those hundreds of objects, every single frame. So you have a very unpredictable workload. There could be a few objects in the car, or there could be 100 objects in the car. And you have this really big follow-on workload that you need to run within one frame in order to complete it in time. So this is a great use case for our Mythic quad amp. You can put a single object detector on one of the chips, and then you could put the follow-on classifiers on the remaining chips. Or you could take 2 of the chips and run an HD resolution 60-frame neural network and have the other 2 chips run the follow-on classifiers. There's a lot of different ways that you can play with the flexibility here. And this is kind of an easy way of thinking about the difference between the 2 cards and thinking about what does more tile capacity get you. And this is, again, what's really great about our architecture is this easy scalability. So with our single chip on an M.2 AE key right here, you can still partition that architecture. So you could have a 600 by 600 object detector running at 30 frames a second, and then you can do a follow-on classification of maybe 100 objects per second, depending on the classifier being used. Or you could use our quad amp card. Now you can run a full HD object detector at 30 frames a second, and you can run higher accuracy models, and you can do follow-on classification of thousands of objects per second. You know, maybe with that HD resolution, you're now seeing many, many, many more objects. On top of that, you can pack in a whole variety of different classifier models. Maybe you have a classifier model for cars, a model for buses, a model for trucks, a model for pedestrians. And finally, you could even throw another neural network on top of that, like semantic segmentation, all running concurrently in parallel. So this is that scalability of our architecture and of our product that has been really appealing to customers. So this is 4 copies of YOLO v3. And this is in a room. And you can tell this was just recorded at the same time I'm recording this now. I'm wearing the same shirt. Now, this just happens to be 4 identical copies of YOLO v3. This is the off-the-shelf YOLO v3 trained on the COCO dataset. But this could actually be 4 different trained models. You know, if you think about like a drone environment, you might have one camera facing forward, one camera facing down, and maybe one camera facing behind you. And it might be advantageous to have different classifiers trained on those different perspectives that those cameras have. And you can do this with the quad amp card. So now I'm going to talk a little bit about software. So the front end of our software tools is the Mythic optimization suite. So here you can quantize the model to int4, int8, int16, or analog 8. You can also prune down the model if you need to hit a more aggressive latency target, and then run a retraining step in order to recover the lost accuracy from the pruning and quantization. Then the back end of our tools is the Mythic graph compiler. So this is a totally push-button suite that takes the Onyx model and converts it into a runtime that's ready to run on the silicon. It performs all of the mapping, optimization, and code generation in order to hit very aggressive latency targets. And you don't have to write any code, and you don't have to do any hand tuning. And I think the most incredible thing about Mythic is that we built this very capable software flow on top of an analog compute product. And that took a lot of innovation and a lot of new ideas in order to pull that off. We also offer a library of popular models that are already set up to use our entire software flow. So we've taken public open source models and packaged them up to be really easy to use with the Mythic hardware platform. So this includes object classifiers, detectors, pose, segmentation, and depth estimation. And now I want to talk about what I think is one of the most exciting things about Mythic, and that's our long-term roadmap. You know, we're just getting started with our 40 nanometer product series, and we have a lot of other things in development that are going to be really exciting, including a 28 nanometer product, and even some stuff further out than that that is going to really broaden the scope of what we can deliver with analog compute. So this is a generational technology. It's going to be around for a long time. It's going to be incredibly powerful. And Mythic, we did a lot of the pioneering work to make analog compute a reality. So stay tuned. Follow us on social media. You'll see us at all these conferences. We're going to have a lot of really exciting news to come. So thank you for listening, and I look forward to questions at the end of this session.
Cool. Thanks, Mike. Exciting to see a session. Welcome back.
Thanks.
Cool. We've had quite a few questions come in, so I'm going to try and group a couple actually that are around power and efficiency to start. Okay. So the first question is, with such low power, can you envisage training at the edge?
That's a good question. So, at the moment, I wouldn't say we see a strong customer demand for training at the edge. That might come down the road. And even then, it's a question of how much real-time performance do you need for training at the edge, or can you do it kind of in the background? Now, just in general, the topic of training with analog compute, there's a lot of academic work going on in that. It's certainly a very compelling future horizon. You do need a different memory technology. The flash won't work for training with analog compute. That being said, there's actually a tremendous amount of work happening on developing new non-volatile memory technology specifically for analog compute. And so, I'd say the very long-term horizons are very bright for that, but short-term, it's likely going to be an inference world for analog compute.
Okay, thank you. And then the next one's from John, which is around efficiency and power. It's quite long, so there's a statement and then a question. So John says, So when he was working on analog edge AI for DARPA around the 2009 time, he found that digital to analog and then analog to digital conversion dominated the power. And then he goes on to say, it's almost certainly become more favorable now, but how much power efficiency could you gain with a fully analog signal chain?
Oh, well, okay. So, well, to answer the first thing, there's two aspects happening here with, comparing analog to digital. And yeah, during the DARPA days, there was like DARPA Upside and Synapse. There was a lot of work happening on analog compute, and those efforts were looking, very kind of zooming in quite a bit on the multiply accumulate math operations. Whereas you really have to look at the whole system and say, if you're building a digital system that needs to store hundreds of millions of weights or something like that. And you have to pull them out of DRAM and you have to bring them into the compute unit and you have to have all that coordination happening. You might have parallel and concurrency happening. That's just hammering the memory interfaces. That's where you really, when you see that whole picture, then the comparison starts to look a lot more favorable for analog compute. Just looking at the multiply accumulate alone can be a little bit misleading. I think that the second aspect is that people were way overdoing it on the A to Ds and D to As back then, and there's actually a lot of tricks you can do to need a much narrower range of dynamic range. But they were trying to almost replicate like the full dynamic range, which would be very difficult to do. The last point I'll make is that there's a lot of tricks you could, if you start thinking about building a chip with tens of thousands of ADCs on it and DACs, there's a lot you can do to amortize across the whole chip. And that's a very, that's an area that's not very well known or researched outside of the analog compute world, but we spent a lot of time digging into that exact aspect and got a lot of savings from that. Doing a full analog chain, that just quickly destroys the signal. And I've seen some approaches where you can specifically train for the chip you have and have a full analog signal chain, but training per chip is not very practical from a go-to-market perspective. Like your customers want one binary, they just push to all the devices.
Yeah.
So I don't see that really, in our world at least. Maybe in some other worlds it might be a thing, but not in ours.
Okay. Cheers, Mike. Another question is around benchmarking. So have you benchmarked your solution against spiking computing approaches?
Yeah, and I mean, well, it's not really, they don't really live in the same worlds. So where we've seen spiking neural networks really do well is on things like time series data, but at the same time, I've never seen like an apples to apples comparison of like, here's some data or here's a use case that spiking does extremely well on. Now here's the best attempt at building a deep neural network for that same thing. I've never actually seen that, nor have I seen a case where spiking does anywhere near as good as deep neural networks for, the conventional use cases that everybody uses deep neural networks for. So without that kind of apples to apples comparison, it's really tough to benchmark.
Cool. Okay. John, for the last question, said good answer. Thank you. So some feedback there. Thanks, John. It's the last question before we go on to the next session. I guess on that point, just, I think we all know that analog compute in some way, is part of our future in accelerated computing. So when do you see that inflection point coming? And is there a couple of things that you think are going to be important in triggering that?
Yeah, it's a great question, actually. So, it's been, so analog compute there actually was a very, as I said in the presentation, there was actually a rich history of products in the 50s and 60s, but the recent wave of analog computing, it is quite academic up until, maybe the 2015-16 timeframe. At that point, I think the companies that got venture funding to do analog compute really helped. There's just been an explosion in academic research. Now, a lot of conferences have entire tracks dedicated to analog compute. every professor I know who would have skills in that area is now researching it. But I think in order to truly hit an inflection point, you need the first product out, and it needs to be successful. Then you see the real explosion of interest in it. You'll see big companies and small companies also go steaming in. I'm going to give one example of what would look like past that world. Is that right now models are very optimized for heavily memory constrained systems. It's like depth-wise separable, things like that. In an analog compute world, you actually have a lot easier access to memory. You might see model topologies that are totally different and optimized for analog compute. That's what it would start looking like, I think.
Okay, awesome. Well, thanks, Mike. It's good to have you back with us. And yeah, I guess I suggest connecting with some of the people with the questions to have further conversations. And thanks everyone for these questions. Up next, we have we're going back into roundtables now. So there's 3 roundtables concurrently. So please do sign into them and actively participate. And thanks, Mike, again. And we'll move on to the next session.